Okay, I have to do something because that just blocks my view. So just a second. Okay, I don't know how to do that. Okay, so last time we concluded the lecture by producing infinitely many pairs of smooth four manifolds which are homeo but not diffeo. And if you remember, I advised you to take these surfaces, hypersurfaces in CP3 at the S's with an odd parameter, and as a counterpart, it was some number of CP2s and some number of CP2 bars, and the homeo was coming from Friedman's fantastic theorem saying you only have to check Euler characteristic signature and type, and if they match and they happen to be simply connected, then you have homeo, and non-diffeo came from Seiberg-Witten, and in particular two famous theorems, the vanishing and the non-vanishing theorem. So vanishing, that the Seiberg-Wittens are always 0 for these guys, and the non-vanishing, that the Seiberg-Wittens are never 0 for the other side because they happen to be symplectic, as they are Kähler manifolds because they are complex submanifolds of Kähler manifolds, namely the CP3. So today we would like to do, I would like to give you a recipe to generate infinitely many different smooth manifolds, which are all homomorphic, but pairwise not diffeomorphic. So infinitely many x's, x1, x2, and so on, all homeomorphic, but pairwise non-diffeo. Of course, as always, the proof will be very incomplete. I will just give you an idea how this thing works. And of course, again, homeo will be done by Friedman. So that will be a consequence of this simple calculation of Euler characteristic signature and sometimes the type. And pairwise non-diffeo will rest on the fact that we can compute the number of basic classes, or I will give you an idea how to compute the number of basic classes, and will distinguish them. So this is sort of a little refinement. It's the next step beyond vanishing and non-vanishing. They all have non-vanishing invariants, but somehow the nature of the invariants themselves will distinguish them. And then we can go even further by taking the value of the Seiberg-Witten function on the basic classes. And there are many more steps, and one can refine this strategy, but today we will sort of content with that. And so here is the construction. So as I alluded to last time, there is an elliptic fibration on E2 CP1. So what does that mean? i.e., so let's give a name to that. Let's call it F. The generic fiber of F is an elliptic curve, which for a topology just means that it's a two-dimensional torus, and there are some singular fibers and can assume that one of them is a nodal curve. Such fibers are called fishtail fibers, and you will understand in a moment why. But let me just recall you that the nodal curve C in CP2 looks like this in homogeneous coordinates. This is the zero set satisfying the following equation: zy square equals x cubed plus zx square. So this is like a very hands-on curve, and it looks like this, where a straight line would symbolize a sphere, S2, and it's a sphere with one double point. So you just take your sphere and you just pick 2 points and you collide them, you identify them. You can compute the Euler characteristic of this thing. It's not 2 anymore because the 2 points are identified. So the Euler characteristic will be 1. And so we can assume that E2, or favorite four-dimensional manifold, the K3 surface, admits an elliptic fibration with typical fibers T2, but some of them are more singular. And among those, we can assume that we have such singular fibers. Let me just remind you how this E2 is defined. So first, we took CP2 and took 2 elliptic curves, 2 degree 3, 0 sets of 2 degree 3 polynomials, which were in generic position. Therefore, they intersect each other in 9 points. Once you blow up the 9 points, they will become separated. So we have a fibration over CP2 after the blow-ups, and the generic fiber will be the corresponding degree 3, which in generic case will be just a T2. And if this curve happens to be singular, there is some singularity, then the resulting fiber will be singular. And of course, we can start, one of our starting curves can be a singular curve. For example, we can just take this guy to be one of our friends, and then the other guy is a smooth cubic, and start with that. So this fibration we can assume that it will have a fishtail fiber, and then we just double it, meaning that we take a small tubular neighborhood of a regular fiber, we take another copy, and then we just glue them together. And that's by definition my four manifold E2. So it will, this fiber will survive this procedure, and then we have a fibration what we would like to see. Okay. Well, what do we do with this fiber? Well, now what's called the surgery operation begins. So this box will symbolize me the E2 four-dimensional manifold, and inside we have this fishtail fiber. So it's a fishtail because if I complete the picture, I hope it's visible, then it's like a fish, and this long thing is the tail, but let's just forget about that. We take the four manifold and we pick that point, the singular point of the fiber. Remember, it's a singularity on the fiber, but it's a smooth point in the four manifold, and we blow that up. So blow up. What do we get? First of all, the manifold will be E2 connected some with CP2 bar. As we agreed, the blow up has the effect of a connected sum with CP2 bar. And now the 2 points of this nodal curve will be separated. So instead of having an immersed sphere, it will be now an embedded sphere. But the blow up also brings in, instead of a point, an entire CP1, which will intersect this fiber in 2 points. If you do this procedure backwards and you collapse this exceptional divisor into 1 point, you clearly see how the 2 intersection points are collapsed to a double point in the singular fiber. A fiber has always homological intersection 0 because you can sort of move it away from itself. So a nearby copy will be disjoint from it. Let's call this homology class of the fiber F, indicating that it's a fiber. Well, if we blow up, then this will correspond, this exceptional divisor will be denoted by E. The self-intersection of E is -1, as the generator in CP2 bar is -1. It's like a projective line, but now we count intersections with the opposite orientation. So instead of having the one point of 2 copies of intersecting in +1, it's a -1. And this will pick up in homology -2E, because every branch will sort of bring in a copy of E. So the self-intersection will be -4. Okay, so this is what we have. And now we would like to do the following. So take the tubular neighborhood of this thing. I don't know how visible it is. I was just drawing a little red circle around this F-2E. Interrupt me if it is not visible, then I will just go back to white. And I would like to replace it with something. So replace the tubular neighborhood of the blown up fiber with CP2 minus the tubular neighborhood of a quadratic curve. A quadratic curve in CP2 is defined by a degree 2 equation. It's not very hard to see that it will be also a sphere. The intersection will be 4. So let me just try to draw something. So this is CP2. This is my quadratic curve, which I denote by Q. And once again, I take the tubular neighborhood and I cut it out. Now the two boundaries will be the same. Will be the same with the opposite orientation, because this is a neighborhood of a -4 sphere, while this is a neighborhood of a 4 sphere. So they are orientation reversing diffeomorphic. So we just take this shaded region and cut out the tubular neighborhood of the curve and glue in the shaded one. Now it's a complete mess, as I see, but I hope you follow what I'm saying. So we consider E2 by definition is E2 minus the open tubular neighborhood of the blown up fiber union CP2 minus the tubular neighborhood of this quadratic. So we get a closed 4 manifold. Now comes the usual yoga. Compute the Euler characteristic. Well, that's not very hard. We took out the sphere and we replaced it with something which have homology. So when we started, we replaced the point with a sphere and then we took away a sphere. So somehow the Euler characteristic didn't change. So chi of E2 is chi of E22. The same holds for the signature. So the signature doesn't change. I will sort of put the question about the type under the rug, because indeed it does change, unfortunately, but it's not so important at the moment. We will return to that. Let's see how the homology changed. So I will just erase this. And remember that the elliptic surfaces come with sections. So there is a section which is just to put together two exceptional divisors in the E1 when we do the blow-ups. So there is a section sigma with self-intersection -2. So we should see 3 homology classes before the blowdown. We have the section, this blown up fiber, and the exceptional divisor. And then suddenly we sort of take away one. Would like to see what we end with. So notice that this E intersects the region what we are taking out in 2 disks. So E was a sphere and we took out 2 disks. So what's left over is an annulus. The complement of the quadric CP2 minus the neighborhood of the quadric has first homology Z2. So we have these two circles on the boundary. They have to bound something. It has, sorry, yeah, H1, Z2. So if you take two circles, which are very close to each other, sort of homotopic or homological, then their union should bound something. And indeed it does. It is CP2, it is the quadric, and we just take a line. And when we take out the tubular neighborhood of the quadric, again, the line intersects it in two disks. So we take this out, we have another annulus. So we can glue these two together. We have an annulus from here and an annulus from the other side, from here. If you glue them together, we get, from this construction, we get E bar. This is now a torus with self-intersection 0, right? The self-intersection of E was -1. The self-intersection of this guy was 1. So you can sort of position to see that the self-intersection will be 0. Okay. What happens with the section? The section intersects this neighborhood in a disk. The boundary circle might not be homologically 0, right? Because it might be the generator. So why don't we take another copy of this, like this, and we take 2 sigma, twice the section. Now it intersects it in 2 disks. Now we can do the previous yoga, and this will give us a homology class. It's sort of harder to estimate what the self-intersection will be. I computed it at home. It's -7, and it's harder to see what the genus will be. Let's put that aside. But let's see what are the intersection patterns. So E bar, so here I take another fiber. Let's just draw it here. This is F. So E bar with the fiber will be 0. I can sort of move the fiber away and they will not intersect each other. What happens with this 2 sigma bar with the fiber? Well, they will intersect in 2 points. And what else do I need? And let's see how many times, what's the intersection of 2 sigma bar and E bar. And I claim that this is 1 because they don't intersect in the E2 part, but they do intersect in the CP2 bar part, since we complete this annulus with the annulus of a line, and we do the same when we complete the leftover 2 sigma inside this complement with another line, and they will intersect there. So that will be 1. So what can we deduce from here? Well, so I did that at home, and here is what you get. So I claim that this E bar is some linear combination of F and sigma, some alpha times F plus beta times 2 sigma bar. And if we multiply it with what? So how is it? First, we multiply it with the fiber, and E times the fiber is 0. The fiber times fiber is also 0, plus beta times their intersection, which is 2, implies that beta is equal to 0. So indeed, from this equation, we don't have to consider that part. And we have that E bar is alpha times F. And now we multiply this. What do we do next? We multiply it with 2 sigma bar. So E times 2 sigma bar is 1. On this side, we get 1. And here we get alpha times F times 2 sigma bar is 2, showing that alpha is 1/2. So miraculously, we had a primitive homology class F in E2. And after we did this manipulation, we created E, which is just 1/2 F. So we sort of reduced, we made us able to divide the fiber by 2 still in integral homology. So that's the effect of what we did. And here is the claim. So I still don't want to switch to the next board.
2 quick questions. Could you remind me what this sigma was again?
Sigma was the section.
Any choice of section?
Say it again.
Any choice of section, or
yeah, any choice.
Matter? Yeah.
Any choice of section has the property that it will intersect the fiber in one point, and this is all what we needed.
And this also proves that the fiber was primitive because you found something intersecting at once.
Yeah, isn't that magical? It proves that the fiber is primitive, and it also proves that he himself is primitive, right? So it's like having a dual guy which intersects you once just does 2 things. Proves that both of you are primitive. It doesn't sound very good in English, but it does. Okay. Okay, so claim the basic classes of E2, 2, and I will explain why I picked this 2 in here, is just plus or minus E bar, said differently, plus or minus 1/2 F. You know, I'm deliberately jumping between homologies and cohomologies. So now these look like homology classes, although basic classes are all cohomology classes. But there is Poincare duality, which in this dimension just identifies age lower 2 with age upper 2. So we can always, using this identification, we can and we always do confuse these 2 notions. Are there any questions? I trust Miriam will tell me if there is any interesting questions. Okay. Let me just spend a very short amount of time arguing why you should expect something like this, or actually that's too much. How can you deduce something like that? So here is the argument. Maybe I will switch board for that. So the computation comes from 2 steps. First step, the basic classes of E2 are easy to determine. There is one single basic class, which is the 0 cohomology class or 0 homology. And indeed, what we already learned, you can sit down and deduce it for yourself. This follows from Taub's theorem, which says that there is at least one basic class for every symplectic manifold, and E2 is a Kähler surface, so it is symplectic, plus the adjunction formula, provided you understand a lot of surfaces inside this E2. And we do understand a lot of surfaces because it comes from CP2 blown up and then glued together 2 copies of that. So you have to do it for a basis, and then you apply in a nice way the adjunction formula, and you exclude all other cohomology classes. So this is based on these 2 theorems, is a doable exercise. And then step 2, we do what we did before for the the step 2 is that the basic classes of any manifold blown up can be computed from the basic classes of X. And the idea is borrowed from the vanishing theorem. You remember this is a connected sum. So we can take my previous picture. We have X minus a disk and CP2 minus a disk, and we introduce longer and longer necks. And back then, we argued that somehow the things will disappear. All the solutions will go home. There are no solutions if this neck is long enough. That was an assumption. It required B2 plus in this side to be positive and to be positive on the other side, which no longer holds. It turns out that the solutions with psi equals 0, which gave us the headache because they were the fixed points of the group action, now help us because every solution will sort of converge to those. The longer you pull, the better you approximate such a solution, and those can be identified by algebraic topology. So this statement tells us that E2 blown up will have two basic classes plus or minus E. And now comes the third step, where we do the same, but now we pull away the -4 curve. This is the neighborhood of the -4 curve. And now the neck will be the length space L41 times the time direction. And it turns out that the same argument works, except there might be more of these degenerate solutions where psi is equal to 0. But again, algebraic topology will help us to identify them. It will be somehow the representations of, we have to relate it to this other. This is CP2 minus the quadric, L41. And both are negative definite, so this vanishing argument doesn't apply. And then we can relate solutions here to the solutions there. It was very sketchy, and it just gave us an idea. And I should point out one thing, that what makes it really work is that when we pull away, these three manifolds are very special. These are three manifolds which admit positive scalar curvature metric. And by some standard differential geometry, the solution spaces for such three manifold cross intervals are easy to understand. We didn't go through this Weitzenberg formula, but that's the key in this conversation. Okay, so, well, we created one new manifold, and I did sweep the type question under the rug, and there is a good reason, because the type unfortunately changes. So what we do is the following. We start the same procedure, E2, fishtail fiber, blow up once, we get -4, -1. Blow up again, blow up this point, we get a -5 sphere, a -2, and a -1, right? This guy used to be this -1, but now we blew up, so it's a -2, and this is the new exceptional divisor. Then we keep doing that. We have a -6, -2, -2, -1. We keep blowing up the original fiber intersected by the -1. So if we do it a couple of times, we'll have a long chain which starts with -p, -2, -2, -2, -2, -2, and then there is a -1. And we have p -2. So you see, if p is equal to 2, then we just have none of these guys, and we have a -4, which intersects this -1 twice. So this was our first example, but it fits into an infinite family. And then we can do the same procedure, blow this down, so replace it with the complement of the quadric, do the same with the first two curves. And in an earlier lecture, we argued that this can be also replaced by a homology ball, and do a little longer, so the -6 and two -2s, and so on. So in this way, there is this infinite sequence of manifolds, and in any stage, create something new, which we can call E2P. And then it turns out that their Euler characteristic is the same, the signature is the same. Well, there are only two possible types, so infinitely many should have the same type. Indeed, if P is even, they are odd, and if P is odd, they are even. I know it's unfair with the even and odd thing, but this is how it is. So E2P is of even type if and only if P is odd. So in fact, we created two infinite families of smooth manifolds such that within the families, they are all homeomorphic. The two families are not homeomorphic because one of them is even and the other one is odd. Okay, so when P is even, then they are homeomorphic to C3P, CP2 connected sum with 19 CP2 bars. And the fact is, a very similar complete argument tells us that the number of basic classes of P is exactly P. So cybervision theory tells them apart. Friedman theorem tells you that they are all homeomorphic. So now we have two infinite families of the promised properties that they are all homeomorphic, but pairwise not diffeomorphic. Any questions? Let me just go on. And so this is where the mess begins. So we already have too many examples. Let me just introduce some more. So suppose that X is a four-manifold which contains a torus, two-dimensional torus, T2, with self-intersection 0. This is just to say that the normal bundle of the torus is a trivial D2 bundle. And do the following. So this is one input, and the other one is a knot inside S3. Out of these two, we can construct a four-manifold XK by the following procedure. We just take X minus the neighborhood of the torus. When I write this, I always imagine that it's an open neighborhood. So the result is still a compact manifold with boundary. And in this case, the boundary will be the three-dimensional torus T3. And we glue S3 minus the neighborhood of the knot. So this is a three-dimensional manifold with boundary. Again, this is an open tubular neighborhood. So this is a compact three-dimensional manifold with T2 boundary. And then we just multiply it with S1. So this is a four-manifold with T3 boundary. This is a four-dimensional manifold with T3 boundary. And we glue them together. And you pick your favorite gluing, provided the meridian of this torus, so the normal circle, should match with the meridian here. So this is not a uniquely defined manifold. Whenever I write XK, what I mean is that you create one of those. There are plenty of choices, and it's unclear whether they will give you diffeomorphic manifolds, and we don't care. Okay, so once again, the claim is that if X is simply connected and the neighborhood is also simply connected, then X and XK are homeomorphic. And once again, the yoga is the same. You just compute Euler characteristic and signature and the type, and then they match. And And then we apply, since we are always in the simply connected case, we just apply Friedman's theorem. And the fact is that the Seiberg-Witten of X sub k is determined by the Seiberg-Witten of X. Any question?
Should that be, Paul pointed out, should that be meridian with longitude written above?
No, it's the meridian of the knot. So it's like in the T3. I hope it's the meridian. Yeah. So this Seiberg-Witten is determined by the Seiberg-Witten of the original four manifold together with the Alexander polynomial of the knot. So once again, this rests on a much, much more complicated pull-apart computational argument, leading to the following statement, which I will write here. If X has non-trivial Seiberg-Witten function and K1, K2 have distinct Alexander polynomials, then xk1 and xk2 are non-diffeomorphic. So this just introduces a whole new word of constructing non-diffeomorphic manifolds. For example, we can start with E2 and we take a fiber inside, which is a torus with self-intersection 0. This is simply connected. The complement is simply connected. So we have at least as many different diffeomorphism types, as many different Alexander polynomials we have. And things are even worse than that conjecturally. So the conjecture is that xk1 diffeomorphic to xk2 should imply that k1 is isotopic to k2 or the mirror of k2. It's known that the mirror doesn't give you a new four manifold, but maybe if two knots are not isotopic or to each other or to each other's mirrors, then the manifolds are different. That sort of, let me put it in perspective. It just says that we pick or only four manifold, the K3 surface. And we would like to understand how many smooth structures this topological manifold can carry. Then it seems to be more complicated than knot theory, or as complicated than knot theory, but we only used one of these square zero tori. There might be others. We can repeat this procedure. And then we have the previous arguments where we did this blowing down procedure. And it turns out that those are always different. So, you know, perspectives are not great. It just says that even if we fix an innocent looking example, then the chaos we are facing is more than what we see in knot theory. And knot theory is pretty chaotic already. Okay, so this is what I wanted to say about this. So how to organize questions and results in this subject? Well, this brings us to the geography question. So let me just write down geography. Yeah, there are many such knots. I will not draw knots now, but maybe we can save it for the discussion, for example. You cannot. No, you cannot do that. There are no other invariants known to mankind at this moment, which would, so if you have two knots, say there is this sequence of Kanenobu knots, which have the same Alexander polynomial and the same Jones polynomial, and you apply this procedure, then all the invariants so far we can compute are the same. Still, we cannot prove that they are diffeomorphic. The four manifolds are diffeomorphic. And we can conjecture that they are actually different, but we have no idea how to show that. So let me try to organize our thoughts. So we have a four manifold. We can associate to it two numbers. Well, we can associate to it the signature and the Euler characteristic. And for some strange reason coming from algebraic geometry, instead, we associate to them some linear combinations of those. 3 signature plus 2 chi is always C1 squared if X happens to be a complex manifold. If it's not, we just define C1 squared through this formula. The holomorphic Euler characteristic again makes sense for complex manifolds. It has no meaning whatsoever for just smooth manifolds, but we can declare 1/4 of the sum of the Euler characteristic and the signature. Notice that it might not be an integer. It's always a half integer. And for complex surfaces, it's an honest integer. Otherwise, it might not be. This is equal to this formula, which happens to be 1/2 of 1 minus B1 plus B plus. So you can see that sometimes if the parities of B1 and B plus are unfortunate, then this will be a half integer, but half of the time it will be an integer. Okay, so we draw everything in this plane, in the chi age C1 squared plane, and there are some constraints coming from algebraic geometry. Namely, if you have a complex surface, then there are two options for you. Either you are on this line, and these are exactly the algebraic surfaces. So I listed E1, E2, E3, E4, and so on, En. Or we have a surface of general type, and that happens to be in this, what is it? It's part of the quadrant, but not the entire quadrant. It is bounded by two lines. One of them is the C1 squared equals 9 chi line, and this is called the Bogomolov-Minkova line, which was mentioned yesterday by Paul. And there is this other line, which is the C1 squared equals 2 chi minus 6 line, and this is commonly known as the Nodal line. And this happened to be discussed by the research talk on Monday. Probably that was on Monday or Tuesday. And all the complex surfaces, minimal complex surfaces are between. Well, in this segment, we can construct symplectic manifolds. I will show you how to do that. It's not very complicated. And what do we know? Well, we have examples for all but finitely many dots which are below this line. This is the C1 squared equals 8 chi line, 8 chi age line, which corresponds to the manifold to have 0 signature. If you are below that line, then every point with finitely many exceptions has a smooth structure and has infinitely many. There are a few in this small region where we don't really know what's going on. If you go to this little angle, then things are less clear. We don't really have we didn't populate all the possible dots with symplectic manifolds. What happens in this segment? Well, the Bogomolov-Minkova theorem that says that there are no complex surfaces here. What happens with symplectics? Well, we don't know. What happens here? The complex surface theory tells us that there is nothing down here. And likewise, Taub's theorem tells us that a minimal symplectic manifold cannot be here. Whether other manifolds with non-trivial Seiberg-Witten invariants are here, we don't know. So there are many questions. It sort of helps you to locate your manifolds in this picture, but there are some questions which are still not known. So let me just list a few
Andres,
Yes?
sorry, there was a question in the chat a while back that I missed. Are there examples of xk1 and xk2 which are non-diffeomorphic, but k1 and k2 have the same Alexander polynomial?
Yeah, so, you know, but, so this is a question, non-diffeomorphic. This is the typical answer a mathematician usually gives for a question. I don't know. We don't know. You know, this is the only input, this is the only information we get out of the Seiberg-Witten equations, and Seiberg-Wittens are the only tools we can distinguish homeomorphic manifolds if they happen to be non-diffeomorphic. So we have no idea. You can try to find a diffeomorphism. People did try that. What happens if you don't find a diffeomorphism? You don't know how to prove that they are not diffeomorphic unless you have some kind of a way to tell them apart. And we don't have any tool for that. The only tool to distinguish non-diffeomorphic manifolds at this stage are Seiberg-Witten invariants or Heegaard-Floer invariants, which happen to be the same, or Donaldson invariants, which also happen to be equal to the Seiberg-Witten invariant. So there is no tool we can use to answer that question. Okay.
Awesome. And there's one more. Do we know any manifolds above the BMY line, maybe coming from algebraic geometry?
So again, so a manifold here, which is?
Are there any manifolds above that line? And they say maybe coming from algebraic geometry? No.
So it's sort of a vaguely posed question. What does it mean for a manifold to come from algebraic geometry? So it's a complex surface, then there is a law, but there is a theorem, the Bogomolov-Mihalko-Yau theorem, that they are all below that line. Whether you can do some construction and end up with a manifold here, I don't know. Of course, you can always do tricks, like you take E3 and you reverse its orientation, and then it will go somewhere here. But suppose you would like to find an example which is symplectic, or at least it has non-zero Witten invariants. No such examples are known. So I did write a few problems. Unfortunately, I'm running out of time, but let me just list. I mean, here I listed a couple of hard problems. So, you know, what are people thinking about, or what are people considering to be important questions? Whether we have an exotic structure on S4 or 2 copies of CP2. This is very hard because we don't have any tool to decide that. Seiberg-Witten theory will not be helpful because it's defined on the second homology, and here the B2 plus has the wrong parity. So these are super hard problems. What about exotica on CP2 and S2 cross S2 and CP2 blown up 1 point? There we do have the tools, we just don't have the examples. You know, what are your candidate potential smooth manifolds which are homeomorphic but not diffeomorphic? We don't have those. But, you know, that wouldn't be such a groundbreaking result if you come up with a potential example. You are able to compute Seiberg-Witten. It has CP2 apart from that. It would be nice to see, but it's not easy. What happens with other simple manifolds like T4, which is a product of 4 circles? This is supposed to be the simplest 4 manifold, and we don't know. We do have the Seiberg-Witten invariants. We have lots of procedures to create new manifolds out of that. What's the problem? Well, the problem is that when you do these constructions, they usually introduce some local fundamental group. For example, if you take this gluing procedure, then in some miraculous way, the fundamental group of the knot complement appears, which then, because we assume that the other side is simply connected, it sort of dissolves. If you would like to have a sort of philosophical, moral reason why the Alexander polynomial of the knot appears, is that the fundamental group locally appears in the 4 manifold, but then globally disappears. And the fundamental group doesn't remember that local appearance, but the Seiberg-Witten invariant does. Now, there is a problem with T4 because it has a very complicated fundamental group, right? It's abelian, but still it's Z to the 4th. And if you do such a local introduction of a fundamental group, you have no guarantee that it will dissolve in the manifold. Or if it does dissolve, it might change it in some way. So here and here, when you take two surfaces and their product, the fundamental group is a problem. There is the 11-8 conjecture, asking what are the topological simply connected four manifolds which do admit smooth structures. We do have a theorem, the 10-8 theorem, which I quoted in my first lecture, but there is a gap between, and the technique which proves the 10-8 seems to stop there, and we don't know how to move on. Maybe the 11-8 is not true. We just didn't find those manifolds. There is the Bogomolov-Miyaoka-Yau inequality for complex surfaces. What happens for symplectic manifolds? Does it hold? We don't know. This is probably, I mean, when I say hard, what do I mean? That people tried for a long time and they didn't get the answer. It doesn't mean that it's impossible, but these are problems which people tried over and over again. Also, you can ask the same for those four manifolds which have non-vanishing Seiberg-Witten invariants. I claim that this inequality holds for minimal symplectic four manifolds. What happens if you ask it for only for non-trivial Seiberg-Witten invariant four manifolds? Maybe it will not hold anymore, or maybe it does. We don't know. So these are typically rather hard questions, and this is not where I would like to stop. I would like to give you a few where you there is a hope you can make some advances. So yeah, so the first one is a constructive question. So we have this fantastic geography picture, and we know pretty much, we are confident with those manifolds which are under the zero signature line. What happens in this region? This between the Bogomolov-Miyaoka-Yau and sigma equals 0 territory was called the Arctic region by Ulf Persson, who is from Iceland. So, for them, it's probably home territory, but still, it seems to be a very complicated issue to find simply connected symplectic manifolds in this region. If you would like to go really Arctic, then try the Bogomolov-Miyaoka-Yau line. There is one fantastic four manifold, CP2 is here, and there are many others. There are many other complex surfaces. They all have gigantic fundamental groups. Try to find a manifold which is symplectic, but has a small fundamental group, preferably a trivial fundamental group. They all have the property that their universal cover is the unit disk, the four-dimensional disk. So you can imagine these are all fundamental groups of infinite order. What if can we find an example with finite order, which is simply connected? How about near this line? I spent a lot of time, maybe 15, 20 years ago, where asymptotically we got closer and closer, but not actually. Can you do that? On the line, say 5 away from the Bogomolov-Miyaoka-Yau, you take all the dots and you find a simply connected symplectic manifold. I think these are doable exercises, not very simple, but hopeful, as opposed to the ones I listed on the other board, which I think are very hard. Let me give you a few more less challenging, or I don't know. Of course, if you don't know the solution of a problem, it's hard to tell whether it's easy or hard. But so we talked about the genus function of a manifold, which is from the second homology to Z to N, and associates to alpha the minimum of the genera of sigma, where
Andras,
yes?
could you move the board, the camera
yeah.
to the board?
Thank you. So we take all the surface representatives of a fixed homology class, and we take the minimum genus. this function is known for CP2. This is the famous Thom conjecture. And so we know that there the second homology is just Z. And if you take D times the generator, then the genus function, let's call it age, is just D minus 1 times D minus 2 over 2. And you can assume that D is bigger than 1. Well, what can you say about CP2, connected sum CP2? We immediately lose the Seiberg-Witten equations or the Seiberg-Witten invariants. So it becomes a very hard problem. To start with, just show the following, that 3, 2, so 3 times the generator here, twice the generator there, can be represented by a sphere, but 3, 3 cannot. Of course, you know, once you do some advances for CP2, connected sum CP2, you could try n copies of CP2 and see first which homology classes can be represented by spheres. If you know that, can we determine genus function that is again complexity 1 higher? And let me finish with 2 more, which are of my current interest. So we take the K3 surface E2, and it contains many spheres of self-intersection -2. We saw that today. It contains a sphere of self-intersection -86. It's not an absolutely trivial fact. It's not very hard to verify. Question: does it contain a sphere with a self-intersection less than -86? We don't know the answer. You know, or current constructions never want to produce anything lower than that, but we don't see any reason why not. So again, this is just playing around with surfaces inside 4 manifolds. And let me ask another question. So let's take a knot K in S3, where S3 is now viewed as the boundary of the punctured K3 surface. So just take out the tubular neighborhood of a point, namely an open disk. The boundary is S3, and you have a knot. Does K bound a disk smoothly embedded in E2 minus the neighborhood of the point? Well, we can verify that statement for many knots. So fact, it does if the unknotting number of K is less than or equal to 9. What if it doesn't satisfy that property? Are there any knots which do not bound the disk in that manifold? So I just wanted to list these problems in this concluding few minutes, just to say that in order to understand 4 manifolds, what you have to do is to sort of open it up, open the hood of the 4 manifold and look into the structure. And in this context, the structure of the differentiable structure of the 4 manifold is the combination of surfaces representing various homology classes. If you do understand them well enough, then you might start being able to answer questions like that. But it seems that we do not understand not even the K3 surface well enough, let alone more complicated 4 manifolds. So if there are no questions, then I think this is the point where I would stop. And I should thank the organizers for inviting me for this summer school. And I thank all the participants to patiently sitting through at the confinement of their home, these lectures. It would be fantastic to be present and to do that together. But as we all know, this is the best substitute we can get at this moment. So we have to use it, and you should get the best out of what we have. So I hope it was useful, and it raised a couple of questions and showed a few techniques you should understand and apply in manifold topology. And I will leave the rest for Aru and Lisa to conclude with topological manifolds and manifolds with boundary. That's it.
Okay, can we thank our speaker? Do we have any questions for our speaker?
Can you say a little bit for the last part? How do you conclude for 9 unknotting numbers?
Say it again.
Oh, the last question, that how do you conclude unknotting number 9? I thought unknotting number is 4 known so far.
Well, science moves on, and then sometimes a 4 becomes a 9. It's a longer story, but it requires a very specific vibration on E2. So today we work with a vibration, an elliptic vibration where we had a fishtail fiber. Well, we require 3 very specific fibers, and then you see how to get rid of these, this is my E2 minus the point, neighborhood of the point, and my knot is here. And I find all kinds of spheres intersecting each other once, but otherwise disjoint. And I take an immersed disk. Can you see what I'm saying? And if you find sufficiently many of these pairs, then you can get rid of the self-intersections. And you have to vary a little bit. How do you get 9? This is what I did. I was worried, and then I realized that there you can do 9. How about 10? I have no clue. This technique will definitely stop there. So, it's an open challenge. I should mention that the problem is not to show that there is a knot with unknotting number 10, which bounds a disk, because there are slice knots with very high unknotting numbers. So for example, show that all unknotting number 10 knots bound the disk, or preferably all knots bound disk, or something like that, or all torus knots bound disks, or I don't know, satellites, or something like that. So, the problem
is the number 9 somehow related with like number of CP2 bar in E1, or the number of sections in some sense?
No, I don't know, but this is a good approach. Whenever you see 2 numbers, let's hope that they are related. And sometimes they are, sometimes they are not. This 9 has nothing to do with the CP2 blown up 9 times. Not that I see the connection. 2 9s, they are not suspicious. If it would be like a 7-digit number and there would be another 7-digit number and they are equal, then you should suspect that there should be some relation. 1-digit numbers, there are not too many. So, yeah, I don't see the relation.
And for example, if you move to E3, then can you say, like, can you increase the unknotting number in a better way?
For E4, I wrote it down, and I don't remember how much do we get. For E2n, we get unknotting number at most 9n. But maybe all knots are sliced in the K3 and in all of these E2n's, or actually in all EN's. We don't know. So yeah, it's just, so you will have a discussion session today with Stefan, and I don't know, do we have for this course discussions tomorrow? If you cannot sleep throughout the night because you are so much hooked on like what fibers do you have and how do you do this kind of thing, just let us know. Stefan would be very happy to discuss how to create specific fibrations on E1, on E2, and Marco, actually this problem I learned from one of his lectures, so I'm sure he would be very happy to talk about that. So this is not a commercial break though, but if you don't have anything better to do, why don't you just visit the TA sessions and they will give you a little more feedback. Okay?
Okay, I think I'm going to cut things off there just so we can kind of stay on schedule, but can we give one final round of applause for an excellent introduction to the geography problem, constructing exotic form manifolds? Okay, and then we can take a 5-minute break, and I guess we'll start back at 11:22.